Okay, this repeat screening with the same test is a complicated process, and I want to walk you through it slowly. And we have written everything out so that if you don't understand what I'm saying or don't comprehend it, you can just read the verbiage and hopefully follow along and put the data in the correct cells. So, I wanted you to know that part of the process is that we're going to lower the number of people that we're going to test. And when we use the same test twice, we're going to test negatives. We're not going to test positives. So we're going to test these negatives. Okay? Now notice what happens. The first thing that is we're going to move 830 down to be the total number of people that we're going to test because that's 20 plus 810. Okay, now if you'll notice, we have 20 people from the past who are positive, although they tested negative. So we want to know uh, the incidence within a certain time frame. And as you know, if incidence isn't specified, it's usually annual, but it can be any time frame. It can be 2 weeks, 3 weeks, 4 weeks, 5 weeks, 6 weeks, or 2 months. So don't let that confuse you, but we're going to test the same group again later is the point. Okay, so what we want to do then is, and we don't care about rounding as we go along, so I just want to make that point clear. We're going to take 20 and we're going to multiply that by 1%. And, we're going to take the 1% and multiply that by 830, the total, and that's going to give us 8. So we're going to have 8 here. We're going to add that 8 to the 20 because this is the number of new cases that we're expecting in this time frame is 8, but we already have these cases that are positive, and then we're going to take 8 and add that to 20, and we come up with a total of 28. You follow me so far? And this is the key, and this tells you exactly what I've just said. Okay? Now, to fill in the table, in order to get the total for cells B and D, or for us D and B, we're going to subtract 28 from 830, and that's going to give us 802, right? So the answer right here is 802. And you're going to see this on the next slide. Don't worry about it. I just want to talk through with you first. Then you're going to take the 28 and you're going to look at the sensitivity, and we're going to translate that to a zero point 0.8. So zero point 0.8 times 28 is going to give you an answer of 22. And when we subtract the 22 from the 28, we're going to get the false negatives, which is going to be 6. Okay, now we go through the same process to fill in B and D. And so we have 802. 802 is the answer here. We're going to multiply the 802 by the specificity of 0.9. And when we do that, we come up with 721 cases. Then we're going to subtract 721 cases, which is the true negatives, and we're going to come up. Then we're going to subtract 721 from the 802 to come up with 81. Then we're going to add the 22 plus 81, which gives us 103, right? Then we're going to add 6 plus 721, which is going to give us 727. Now you want to remember this because we're going to do a third screening. So we're going to pull this number down, and it's going to take the place or position of the 830. Okay, so what we're noticing, we started from 1,000, we have gone to 830. We know that our false negatives is now declining. So we went from 20 to 6. So in doing that with a second screening test, we are identifying those that tested negative who really have the disease, and we're interested in those people in particular because they spread disease without the rest of us knowing that they have the disease. Okay, now this tells you everything I said about how to complete this particular table. All right, so if you've had trouble following me verbally, or I've gone too quickly or whatnot, you can go back through and fill in this table. Okay, so you come up with the same answer. Now the question becomes, well, how about a third screening? Can we do that? Yes, we can. We can do a third screening with the same test. So when we do so, we're going to test again. When we use the same test, we're going to test negatives. So we're going to look at 727. We're going to pull that down, and I'm going to show you that in just a second. And then we're going to multiply incidence times this value, which the incidence is 1%, and that's going to give us 7 because we forget the rounding. And then we're going to take that 7 and add it to 6, and that's going to give you, watch, that's going to give you 13, right? Then we're going to take the sensitivity, which is still 80%. We're going to multiply 0.8 times 13, which is going to give us 10. We're going to subtract the 10 from the 13 to give us 3 false negatives. We're also going to, now I altered the order a little bit. I didn't do the subtraction here first, but we could have. We can take 13 from 727 to come up with 714. Then we're going to take the specificity of 0.9, and we're which would lead us to, okay, the specificity of 0.9, which is going to produce 643 false true negatives, I should say, and then we're going to subtract these two values to come up with 71. So then we're going to add them across. 10 and 71 would be 81, 3 and 643 would be 646. Now, what I haven't mentioned thus far is we could do PPV, positive predictive value, negative predictive value. We could do it for every one of these tests. We can do yield. We can do accuracy. We can do validity. We can do any statistics we want about this test. But what I want you to see is we've started at 1,000 total cases. We've dropped from 830. Now we're down to 720. Now this is the value we're going to be focusing on next and taking into account in our table, right? So our next table would be, well, I guess I've shown you this table, but if we were going to concentrate on it, the next testing would take 646. Now, what I'd like you to do is I've done the next, we have done a total of 9. I would like you to do the repeat screening for test 10 through 15. So you would have those tests that you would do. You continue with this data, and then I want you to draw some conclusions. So you would complete test 10, test 11, test 12, 13, 14, and 15. So you do 6 on your own, going through this process so you really understand it. And then I'd like you to tell me when you would quit screening and why. Now, let's say that you're a public health director or you're a person in charge of screening. I'd like you to tell me when you would quit repeat screening and why. And two criteria that I'd like you to, a couple of criteria I'd like you to take into account is cost. You know, where do we lose cost benefit? And you got to have personnel to screen other people, and then the seriousness of the problem treated. So if you had a rare disease, I shouldn't say a rare disease, a death, a disease with high mortality, you might want to screen longer than you would otherwise. Now, I want to give you the answer to this particular question because I'm going to have you focus on, I said what was the most important was the false negatives. And the first question I want you to find out or determine is, does a false negative number change very much with additional testings? Well, we look here, 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 and it's not until the 9th testing that we get to 1. And then you can look at the additional testings that have gone on. Now, a benefit is our population, or the total number of negatives that we've tested, is becoming smaller, right? It keeps getting smaller and smaller and smaller and smaller, but we're spending money throughout this entire process. It's costly. It's costly to have people screen. You're still dealing with a large number of negatives. Okay? So you're to tell me when you would quit. When would it no longer be effective? And my answer would be, probably around test 4. But you could argue maybe for test 3, because you're not getting a lot of gains in false negatives, and you're still spending a lot of money, but you are gaining one more false negative, and you are more confident in your true negatives. So either 3 or 4 would be a good quitting place, but I still want you to use this criteria, this criteria listed here, and go through and write something out that makes logical sense to you as to when you would quit. Okay? And promise yourself and take the time to go through this process, because you can get confused so quickly and so easily that you won't know how to do it in a quick amount of time. So I just ask that you help yourself and make it easier upon yourself. Now I want to draw a conclusion, and I've tried to write things out for you so you don't have to depend so much on what I say, because I've done it, and sometimes I leave out steps because I'm more familiar with it, and it's confusing if you don't do it routinely. Now, the statement, do you ever get to 100% of the false negatives? Well, I can tell you it would take many repetitions of repeat screening with the same test, which would neither be cost beneficial nor practical. You'd have to have a whole team of people doing this screening, and it would cost a lot of money. Where do you just stop? Here's the school answer. Where you stop repeat screening depends on the seriousness of the disease and cost of additional screenings. So if you've got a serious disease, you may be very interested in the false negatives because you don't want them to spread a lethal disease that, especially in a population that has no herd immunity. And every time we get a new disease that enters this country for which we have no cure, we are exposing a population that has no immunity, and we can expect higher mortality. Okay. Now, this is another type of screening, and I want to go through this with you, and I want to go through it very carefully. If you look at this, we're looking at diabetes. We're looking at diabetics, and we have two different tests. We have a blood sugar test, and we have a glucose tolerance test. If we just review and look at the data, we can see that test 2, now these are two different tests. These are two different tests, as it points out right here. And you're going to give a second one after time has passed. And I want you to just focus. You can see that the sensitivity and specificity, which are the hallmark of the quality of the test, are different. The sensitivity and specificity here are lower than the sensitivity and specificity here. Now, what's the best sensitivity and specificity you can get? That would be 100%. But rarely do we get tests that are perfect, that would place everyone into cell A and cell D. Now, the benefit, we've gone through this same process, and if you had none of the data and I gave you 10,000, you could figure out, and I gave you the prevalence, and you could figure out the prevalence value, and then you could do the sensitivity, and you could come up with this value. And if I gave you, you subtracted these two, you come up with the total here, and you take specificity, and that would give you this value, and you could complete this table, right? So you'd go through and follow the same procedures. Okay, now with the second stage screening test, you're testing positives. When you use the same test, you're testing those who tested negative based on the test results. And I'm always, when I'm making that statement, that's what I'm meaning. So in this case, what we have done is we've tested, we're going to retest the positives, and we're going to go, and our first rendition shows us that we have a total of 2,250 who are positive. Now notice what happens in the second testing. We go from 2,250 people, we go from 10,000 to 2,250 people. Now, to fill in the table, you would do the same thing. You would take the prevalence, and the prevalence has not changed, so that would be 5%, and you would multiply the 2,225 by 5%, which would give you the number of positives, including true positives and false negatives. Then you'd subtract the two, and then you would take again the specificity and multiply that by 90% to come up with this value. You'd subtract these two to come up with this, and then you do the addition to come up with the totals. All right? Now, let me just say, I want to make a few summary conclusions there. You can see what I've dropped down. You take this data completely in its entirety and you drop it down. Okay? And I want to talk to you about second stage screening. We're using two different tests after a time has passed, all right, because we're still interested in incidence. We don't do the two tests concurrently. And then I want you to examine the quality of the tests, and we usually do that by looking at the sensitivity and specificity, and you can notice that the sensitivity and specificity are lower here in test 1, which is for blood sugar, than it is for the glucose tolerance test, which is 90%. Now, rarely do we get a test that is 100% in terms of sensitivity and specificity. It's not impossible, but it doesn't happen that often. And look at the difference in the validity. This is only getting about 50% of those people that are being correctly classified as true positives and true negatives, and this one's getting about 80%. Now, when we use a second stage screening test using another higher quality test, we're testing positives. When we're using a screening test or the same test more than once, as I mentioned, we're testing negatives. And in order to do this, to complete this screening, we take this complete set of numbers and from the positive, and we complete them here. Now, in order to determine what the number of true positives are, we're going to take 350 times 0.9, and we're going to come up with the true positives. We're going to subtract 315 from 350 to come up with 35. We're going to take specificity at 0.9. We're going to multiply that by 1900, and we're going to come up with this value. We're going to subtract these two values to come up with 190. Then we're going to add across to come up with 505, and then we're going to have 35 plus this value to come up with this value. Now notice what's happened. We started out with a population, or total population of 10,000, and we're down to about 20% of those, a little over maybe 22% of those people that we really need to test again. That's a wonderful benefit of the test. Now, we can use a combination of tests. We could use a repeat screening test. We could use this test on more than one occasion, and then finally use this one. And then we would test both the false negatives as well as looking at those that are positive again. Okay? Now, I hope that's clear, so you can combine the tests if you'd like. Now, I want to draw some final conclusions about this. Notice with repeat screening with the same test, I showed you alternate tests just a second ago. You are testing those who tested negative. When you use a different and better test for the second screening, meaning higher sensitivity and specificity, you are testing those who tested positive. Okay? I've got another exercise that is difficult. It's been noted to be difficult, but I'd like you to understand it right along with me. What we're going to do is we're going to be involved in changing the cutoff point. Now, you know about cutoff points and blood pressure and whatnot. We could change the cutoff points in terms of an exam. In engineering, they talk sometimes about 92 and above, or 94 and above as being an A. And generally, the traditional scale is 90 and above is an A, although we use pluses and minuses now at Purdue to further discriminate. But what I'd like to do is I'd like to move the cutoff point to the right. I'm going to move it over here now. And so, in other words, I'm going to make the test more conservative. We are going to have fewer A's and B's, and we're really increasing the number of lower grades that we're going to have. But we have greater assurance that those in these upper groups really belong and are homogeneous. In other words, you reduce In this particular case, we reduce the number of false positives, those people who really do not deserve the grade, the A grade, and we reduce the true positives. So this group of true positives becomes very homogeneous. So that's what happens to the impact, and I want to show you this on a table, and I want you to be able to discern what happens when you move a cutoff point to the right, and we're going to now look at moving a cutoff point to the left. So in this first process, we just moved the cutoff point here. We moved it to 92 or 94%, and we became a lot more conservative. So we decreased our false positives, we increased our false negatives, and we increased our true negatives, and we reduced our true positives. So you can see that I'm working across on this particular diagram to help you come up with the interpretation. Now what I want to do is I want to make the test a lot more liberal. Let's say I drop it to 86 or 84 is going to be an A. So I'm going to slide the cutoff to the left. So we have less assurance that the true positives really represent those people of superior, who are superior performance. That there may be a big difference in the performance level, but all will be recognized equally by us being more liberal. Now, what happens here is the false positive group, and the true negative group increase. So we have more true positives and more false positives. Now, what happens too is the false negatives go down, and so do the true negatives. So you know what I always laugh about this because there's always a debate on what we're trying to do with the grading system. And the engineers are telling you that they're trying to set more critical standards so engineers will all be well qualified, and as a result of using a higher standard, we know those students that are really quality students versus setting lower standards for grades, and we have a lot more uncertainty about the quality of the student and their ability, their knowledge of a particular topic. That doesn't have anything to do with performance, but knowledge is one element. Now, you can think of this maybe as in a humorous way, and somebody once asked, you know what they call the lowest scoring student in medical school or a marginal physician student in an academic program? Doctor. So, but I want you to again be able to interpret what happens to each of these cells as a result of moving the cutoff point. Okay? And then ultimately knowing what happens with sensitivity and specificity. Now I'd like to show you this next graphic, and it's always easier to move across, and you look at true negative and true positives together. So these are all the things that I have said. When you move the cutoff point to the right, true positives go down. We're going to notice, that false positives go down, right? And it's shown here. So it looks like we're missing an arrow, but you can draw that in. And then when you move, then what happens is we increase the number of false negatives, and we increase the number of true negatives, and here's the effect. And you can see the impact on the column if you look at those together, and you can see the impact on sensitivity and specificity, and you can calculate the effect on validity. And I would expect you to just take a minute or so and go through there, and so you understand the relationship of one thing to another. Now, when you move it to the left, when you become more liberal, these are the results. So you have just the opposite of results showing. Okay, sensitivity of the tests goes up anytime you test more people. Or you're going to include more people in your criterion for being diseased. Your sensitivity is going up, and when you reduce the number in terms of true negatives, your specificity is going to go down. So this may take you a little while, but I think you'll find it very valuable to see what happens and whether or not you would want to make those adjustments in a medical or a public health scenario as to whether that would be a wise judgment or not. And we look at, how many people do we want to capture? How many false negatives are tolerable? And what is the cost? And what happens to those false negatives that go undetected? And if they had risk factors for heart disease, we might lose those individuals. So do we want to be more liberal or do we want to be more conservative? So that's the value of this kind of information. Now, I've shown it in a little different way. So some people like this graphic better because you can see it relatively quickly, and you can line it up, and you can just memorize it if you want to. I always hate that because it's better if you can think it through without going through memorizing it, because you're apt to forget it. But some of you have very good memories, and I know that. Now, this is what is usual in terms of a screening test in the way of overlap, which includes false positives and false negatives. Generally, we have true positives. That's this group right here, right? And then we have true negatives. They're normal. And right in this little area, we have the overlap of, what would that be? That would be false positives and false negatives. So this is our error. So we're separating the normal from the abnormal, with a few of the patients not falling neatly into the two categories. So that's one way to show you really what's going on. Now, here's a normal curve, and I introduced this to you because you really ought to have this background to remember it, and remember how many cases you're accounting for, and this is called the Gaussian distribution. And we don't have overlapping curves, which is a peculiarity noted among screening tests that I just showed you. But I thought this would be a good review for you and something that you ought to be aware of. And this helps to think about sensitivity and specificity and how much of the population you want to be able to account for based on the validity of your test, which is made up of sensitivity and specificity. I wanted to talk to you about, sometimes we use observations to collect data. And this is probably the best information I know about variability. And so I wanted to share that with you. And if we're trying to reduce bias and we're trying to get valid information, if we have one patient and one observer with repeat observances, you notice that we have high kurtosis and that the base of the curve is not very broad, so the variability is not very great. We have one patient in many observations at one time. We don't do too badly either. If we have one patient and one observer many times a day, you can see how the variability spreads out, and then you want to know what the true score is. Well, the true score can range anywhere from the mean to several standard deviations, so, or the standard error of measurement. And if you have many patients and you just measure them, you're going to get a Gaussian curve. So if you want to decrease the sources of variation, you're probably going to have one patient and many observers at one time retaking, for example, blood pressure to come up with what the true score is. So I just share this with you because people don't think much about variation, and if you ask them how to reduce it, they don't know that either. And you have a pretty good comprehension here in looking at screening tests and how this information might apply to a screening test and collecting data that would go into each of the cells. This would be another way to improve it, so your sensitivity and specificity and validity would increase. Okay, variation. Okay, so our bias, or error is another term for it, is a function of the following: number of observations, number of observers, number of patients, and the administrator's knowledge of the test. And what we forget is we often assign testing or screening to people who really don't know how to collect data in an accurate way. They're more interested in just getting a general idea of where the person might fall. Do they fall in a dangerous category? They're looking really for true positives and in true negatives. But all of these can impact whether or not you might want to medicate somebody or something, or the white coat phenomena. The above factors are all important to consider when trying to improve a screening test. So, and how to practically reduce bias, change the person's knowledge and experience with the test so they know how to test properly. You know, the American Heart Association has a protocol for taking blood pressure. I know that protocol is more for research purposes, but sometimes we get in such a rush that we don't collect data that is very meaningful, in other words, very accurate, and we don't make the best decision for the patient when in effect it would have taken a few extra minutes to get the best or the most reliable data possible. So when we're talking about reliability, we're talking about repeatability, noticing that that is not necessarily validity, because validity is true score. Is a person's blood pressure really 143 over 97? That would be validity. Repeatability is we get the same result whether it's accurate or not. Okay, I hope that helps you in terms of thinking about those two terms. Now, I want to introduce you to another relationship aspect, and I want to talk about the relationship of disease prevalence to predictive value. And you can see that the prevalence with the disease is at 1%, and it's at 5%. So this says less people are ill, and this says that more people are ill or have the disease. Now, we still have 10,000 cases in each of these cells. Okay? That has not changed. That's what's constant. And the sensitivity of the test and the specificity of the test are held constant. Now notice what occurs when when the prevalence of the test is low. We would expect, logically, that there would be fewer diseased people. When the prevalence of the test is higher, we have more diseased people, and if we use this to be 10%, this cell would increase. And you notice that we have fewer false negatives when the prevalence is lower than we do when it's higher. And when we look at false positives, this is interesting. It increases with fewer people than it does with more people who are diseased. And there's a little change. There's a little change that goes on in terms of the experience of specificity. Now, the positive predictive value is really influenced. So when we're talking about positive predictive value, we're talking about 99 divided by 594, and it drops it to 17%. So in terms of, and it's increased when the prevalence is higher. So the positive predictive value of the test increases remarkably, and we have more confidence in the number of people who really test positive. Now this is this second way that we would test for false positives as a percentage of positive tests. If you go back, we had a traditional method and a non-traditional method. This is a non-traditional method. Now look what happens to false positives. The false positives, when we have 1% prevalence, really increase. Okay, so this really increases. So that's not a good sign. Now, when prevalence increases, then false positives go down. Now, let me say something after walking you through this. I know this has been quite a mental exercise, but I want you to get that. I want you to get these relationships, but more importantly, on a practical standpoint, you and I don't have control over prevalence. We don't have control over that. We don't have control over the number of people who become ill or not. But I wanted to show you what it does to the testing, because sometimes you're in a situation where you have more people that are becoming diseased, and if you're dealing with an outbreak and you have an increase, and this would not be an outbreak, but if you had an epidemic and the number of people was increasing in terms of being diseased, this would be the impact on your test, and you ought to be aware of that and the conclusions you might draw. Okay? So that's why I'm sharing that with you. Now I want to show you a couple of other relationship charts because I think they're important for you to know as well. We're going to talk about specificity, of course that has to do with this, and predictive value. Okay? So you notice that we're changing prevalence here, and we're keeping sensitivity and specificity across the board the same. Now what happens to positive predictive value in terms of being able to identify those who are positive? That means these two. It's going to be reduced when the prevalence goes down. And you can see that we split them here, 250 and 250 versus 100 and 400. So we have really reduced the number of positives. Now if you look at prevalence. Now we're going to hold a prevalence constant, and I should be also showing you this information. Well, we hold prevalence constant and we change the sensitivity and the specificity, we just reverse them, you can see again what happens to positive predictive value. This test now identifies more positive people than this test in terms of accurate identification, because if you follow the formula out, that's A over A plus C times 100%. So this is another important consideration for you to take into account. Now, I want to make a summary of what we've covered so far. It says, what happens when you increase prevalence, assuming that you could and you can't make more people sick, and observe the effects on positive predictive value and false positives? They go like this. Prevalence goes up, positive predictive value goes up, and false positives go down. Okay? So that's good that we have fewer false positives. That's wonderful, right? That means we have more true positives. Now, what happens when you increase specificity and observe the effect on positive predictive value and false positives? Well, specificity goes up, positive predictive value goes up, and false positives go down. Now, what are the two ways to reduce false positives? You can increase prevalence or you can increase specificity. Now, if I ask you in practical terms, which one can you do? You can't increase prevalence. So you have to go about ways to reduce variability. That's one way to improve your test. Knowing how to give the test and administer the test, and I can't tell you how often the government has not trained people properly to give a test and then publish the test results and then given the same contract to the people who did a poor job. So if we want to have confidence in our science, we have to have confidence in how data are collected, and that's going to lead me to the very next area, is problems with data collection.